To transform a simple image into a realistic racing car, you might think we need complex physics or intimidating collision equations that turn game development into a mathematical nightmare. But the secret is this: if you've learned how to make a plane fly in our previous project, you already hold the keys to building a professional-grade racing game.
This is the real level up. In this series, we will build this engine step by step. Let's begin. Here we are in the main activity, and the set content function is also empty. Let's start by creating the first UI and call it race activity. It will show up in red because it's not defined yet. Let's create a new file with the same name and define it there. And don't forget to add the composable annotation so the function becomes a UI function.
We will start by displaying the car image just like we did in the Jet game, and that's not just a comparison. Let's open the plane game file. I remember that inside the show Jet game screen function, it started from line 238. So, let's go down. 150, no. 200, and here we are.
Great memory.
Let's copy the code and take it to our new game. This part is responsible for showing an explosion image over the plane, so we won't need it. It's clear we will use a canvas to draw the car, not the jet. The first thing we need is to assign the image to a constant of type image bitmap. This type allows us to display and edit images. To access the images like in the previous code, we will need the context. So, let's copy the two constants. Let's replace the jet image with the car image. And don't forget to change the constant name.
If we take a look at the resources folder, we can see that the cars are just regular PNG images. They are medium-sized, featuring a transparent background, and the image boundaries fit perfectly around the edges of the car itself. Back to the code. Instead of using the same old method, we will use a new format to display the images. Rather than manually entering the canvas and calling save and restore functions, with the risk of forgetting one of those lines, we will use withTransform. This function simplifies both steps, meaning any modifications we apply will only affect the elements inside these brackets. The first modification, just like in the plane game, is setting the drawing position to the center of the screen's width and height. Width first, then height. The second modification is the scale of the drawing board. We will reduce the width and height by 45%. As for the pivot, we will explain its function during execution for better clarity.
Now, all that's left is to display the image using the same function inside the brackets to apply the modifications we wrote. As you can see, the new code is simply a refactored version of the plane's display code. Before running the app, let's set the background to white. To make the screen suitable for gaming, we'll set it to landscape mode by adding this line to the manifest. Then, we'll head to the themes file to ensure the selected mode is no title bar. Everything is ready for the first trial. Let's run it. As expected, the car appeared exactly in the center.
Before we continue, let's go back to the pivot point. What would happen if we removed it? As you can see, the car moved far from the center because the code lost its compass. Instead of scaling around the new center we defined, it tried to scale relative to the original screen center, which is far from its current position. This conflict in reference points is what caused the car to appear in an unexpected place.
Next, we will need a steering wheel.
Oh, steering wheel! Oh, steering wheel! Oh
yes,
yes,
I
I
want
want
a
the steering wheel.
wheel.
Do do do, boop womp. Sorry, I got too excited. Alright, just like the car, the steering wheel is an image, but we will display it using the image function from Compose. For this function to work, we must first pass the image ID and then provide text for the content description property. Let's just add steering wheel. Now, let's adjust the size to a suitable 180 dp. To make this image appear at the bottom of the screen, we'll add the align modifier. The reason it's showing up in red is that the element using this modifier must be inside a container like a box or a row. So, let's add a box at the beginning of the code and set it to fill the entire screen. Now, let's complete this by specifying the bottom section of the screen to display the image. We'll also add some padding so the image doesn't look stuck to the edges of the screen. Let's run the code. And there we go. We have a nice steering wheel and a racing car. Nothing unusual so far. To make the steering wheel rotate, we will add the rotate function. And instead of giving it a fixed value, let's define a variable and call it wheel rotation. To ensure the image tilts whenever this value changes, we'll define it using remember and mutable state of, setting its initial value to 0. Now, all we need to do is change this variable's value while the user touches the steering wheel to make it spin. For this, we need the pointer input function. We can simply copy it from our previous Jet game. We don't need the explosion part this time. This function acts as the sensor system that monitors everything happening on the screen.
This function provides us with two variables at every single moment the finger moves. The first is change, which holds the details of the current touch, and the second is drag amount, the amount the finger has dragged. Unlike last time, we will use the change variable and replace the other one with an underscore. After that, we will write change.consume function, which tells the Android system that we have consumed this touch event for our current logic, so no other background container needs to process it. The mathematical principle we are applying next is very simple. It's calculating the difference between the starting angle of the drag and the ending angle. Pay close attention here. When users place their hand on the steering wheel and drag in a certain direction, they create two distinct angles with the center of the wheel, one for the previous moment and one for the current moment. All we have to do is calculate the difference between these two angles to determine how much we should rotate the steering wheel image first, and then the car. Now, let's start with step 1, which is defining the center of the steering wheel. We will do this using two constants that represent the midpoint of the available width and height in pixels.
Second, we determine the final angle in degrees. To do this, we must understand that the coordinate difference between the current touch position and the center represents the sides of a right-angled triangle. To convert these distances into an angle, we use the inverse tangent function, addn2, which calculates the angle in radians. Since radians are difficult to interpret programmatically in our context, we use math.toDegrees to convert them into familiar degrees, and then we cast the result to a float. Step 3 is to do the exact same thing, but with the angle of the initial touch. By using change.previousPosition, we are essentially traveling back in time for a fraction of a second to find out where the user's finger was in the immediate previous touch, and we calculate its angle relative to the center as well.
And here we reach step 4, which is the core concept of the entire rotation mechanism. By subtracting the previous angle from the current angle, we get the delta, or the amount of change in the angle. If you move your finger clockwise, the value will be positive. If you move it counterclockwise, it will be negative. This difference is the amount of rotation we want to apply to the steering wheel.
Now it's time for application in step 5. We add this new difference to the current steering wheel angle, wheel rotation, to make the wheel turn. Let's test it out right now. Look at that. The wheel rotates during the drag in both directions. However, our first problem is that the wheel needs to return to the center position as soon as the user releases it, ensuring better control during gameplay. The solution is simple. All we have to do is reset wheel rotation to 0 inside the on drag in block when the user lifts their finger off the wheel. Now, let's test the code. Perfect.
The other problem is that there is currently no limit to the rotation degree of the steering wheel, which could lead to strange behavior during the game. To correct this, we will add a constant named max steering angle and set it to 90 degrees as the maximum rotation limit. To apply it, we go to the final line where we update the steering wheel rotation and add the coerceIn function to set a maximum and minimum boundary. This ensures the steering wheel stops between positive and negative 90 degrees. Let's try it now. It looks much more logical and smooth.
The only thing left is for the steering wheel to change the car's rotation. Trust me, this is easy, but there are a few mistakes we need to go through first. You'll see what I mean. So let's head to the code. First, let's define a variable to hold the car's rotation value by copying the steering wheel's rotation variable. Then we add the rotation property and pass this variable to it. Finally, we update the car rotation value as a 6th step right after updating wheel rotation, but we will only take a small fraction of the steering wheel's rotation value, so it matches the car's turning radius. You might think this will do the trick, but the visual result here is catastrophic. The car won't turn like a racing car. Instead, it will fly in a wide circular orbit around the center of the screen.
Yes, and that is because we need to precisely define the center of rotation by setting the pivot point to offset.0 inside the rotate modifier. But even after doing this, the visual result will look like a broken door. When scaling, we will see the car rotating awkwardly around its front left corner rather than its actual center.
The final solution step is to add this line of code, which offsets or pulls the car image backward by half of its width and half of its height from the top left corner during drawing. This adjustment places the heart of the car, or its geometric center, perfectly on top of the offset.0 pivot point. Let's try the code now. This is exactly what I'm talking about. Now we have a car that can be controlled smoothly via the steering wheel. Fantastic.
This is just the beginning. In the next episode, we will continue uncovering more secrets to build an exciting racing game.
The full project is available on GitHub, link in the description, where you can download it easily. We apologize for our long absence, but making and editing these episodes is difficult, and we are still quite new to this world. However, we will do our absolute best to keep going. So, if today's episode helped you even a little,
then hit like. Leave a comment. Let us know you're learning. Next time, we will level up.